All right, so we are moving along in chapter 6, where we introduced confidence intervals. Okay, yeah, and all right. So this is just a little. There's a little section in our textbook. I want to bring it up here as well. So a lot of times when you make a confidence interval, you have some kind of margin of error, right? You want to say, I want to get an estimate of what the mean is. And it's not going to be useful to me if you say, the average height of people is 5'6" with a margin of error of 1 foot, right? And you go, oh, well, that takes me anywhere from 4'6" to 6'6". That's not very useful. Let's say you want your margin of error to be within 1 inch or half an inch or something like that. And so, in those cases, you got to figure out, well, how wide do you want your interval? And it's ultimately going to come down to what your standard error is, right? And so when we figure out what the standard error is, okay, so again, the standard error is the standard deviation of the sampling distribution. And we don't know that exact number because the standard error of the sampling distribution is sigma divided by the square root of n, but sigma is the population standard deviation. That's unknown to us. So we estimate it, right? We estimate it using s divided by the square root of n. And so this standard error is going to depend on basically two major factors, or really just two factors. One is how big your sample size is, where if you have a large sample size, if you have a huge n, your standard error is going to shrink. And also is just how much variation there is in the observations, right? So if you're talking about what's the mean weight of a coin, like mean weight of a quarter, there's not going to be much variation from one quarter to another, right? If you look at a whole bunch of coins and you have this very precise measuring scale, they're all going to be very, 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 very close, like within like a percentage point of each other. Whereas if you talk about the variation in people's weights or people's heights or something like that, there's a lot more variation. So, it depends on the variability of the observations and the sample size. And so if you want a confidence interval with a certain width, certain confidence level, you kind of have to solve backwards. There's a few moving parts here. And you got to, really, the only thing you really have control over is how big your sample size is. You don't really have control over the amount of variability that exists within the sample or exists within the observations. But you do have control over how big your sample is going to be. So, so basically, you've got some kind of margin of error, right? You want it to be within plus or minus some value. And that margin of error is a combination of your critical value T star times the standard error. Okay, so you have basically your desired confidence level will determine T star, but also your desired standard error. Okay. And so to get this, unfortunately, as far as doing a preliminary, figuring out your sample size, you have to just guess. You have to guess. Oh, this should be standard deviation, not SE, but SD, okay? Guessed SD. You have to guess how large the standard deviation of the sample will be, right? And so this guess, hopefully is going to be informed by other information you have. So hopefully, you'll be working with a subject that you have some familiarity with, okay? And so you can say, it's probably around, 3 inches or 4 inches, the standard deviation, or the standard deviation might be around, 3 grams, or the standard deviation might be around, $1,000 or something. You're just kind of guessing this, right? And you're just kind of saying, well, if I take this number and I multiply it by 3, thinking of a normal distribution, we know that around 99%, like almost everybody, 99.7% is within 3 standard deviations of the mean, and 95% is within 2 standard deviations of the mean. So you kind of use those as guidelines to try to guess what your standard deviation might be. And of course, you don't really know. You can also try looking up older literature, right? So anytime you do a study, you should read like other people who've done studies to, on some kind of similar subject or similar idea, similar studies. So you're not working completely fresh, but incorporating previous experience and things like that, right? And so there are a few moving parts. You probably have to do a little bit of guess and check, as if you change your sample size, that's going to affect what value T star you're going to use and things like that from the critical value from the table. And the general rule of thumb is if you've got the money, if you've got the time, try to collect as much data as you can. Okay, but a lot of times you don't have. Well, I mean, almost in every situation I can think of, you don't have unlimited money, you don't have unlimited time, and so you might say, you know what, this is the budget we have. How much data can I collect with this budget? And if you do that, you might realize, you know what, this study with the budget you've given me, it's not even worth carrying out this study, right? Let's say you say, I want to do research on this subject, and whatever your manager, your department says, okay, we will give you $10,000, and you say, well, $10,000, that's only going to give me 20 observations, right, or something like that. Okay, I don't know, right? Because if you figure you've got to hire people, you've got to get insurance for, you're doing some kind of medical study, you're going to be giving people things, and you've got to hire people to do to take the measurements and things like that. You might have to pay volunteers to even participate in things like that. So it might cost you $500 for every single observation you get or something. And so with $10,000, you can get maybe 20 observations $500 a piece. And you go, well, if I only have 20 observations, then, my study is going to result with, at best, my confidence interval is going to look like this. And that's not going to be very useful. It's not even worth carrying out the study. And you could try to argue with your manager and say, I need more money, right? I need to collect at least 50 observations or something. 50 observations, why do you need 50 observations? You have to kind of, there's a bit of back and forth. I mean, you probably don't have to worry about this right now as an undergraduate student, but this could, crop up in your future, depending on what research paths you go down. Okay, so collecting data is an expensive undertaking. And so a lot of times you just end up looking at someone else's data because they spent the money to collect it and things like that. So, thankfully there's good resources. A lot of times our government collects data, and maybe not all the information you need, but there's good resources out there if you know where to look. So, okay, there's another section talking about what conditions are needed in order to kind of apply these methods. So when we talk about these methods, we're talking about confidence intervals, but then also later today, we're going to introduce hypothesis tests. And both of these things, the confidence interval and the hypothesis test, well, today it's the t-test, they rely on the central limit theorem. And we covered the central limit theorem last week, but the big idea of the central limit theorem says that, when you're looking at the sample mean, right, how the sample mean varies from one sample to another, we said that the sampling distribution of sample means follows a normal distribution, right? And you had several homework problems with this, and some of you had questions and about, when do I apply the central limit theorem? When do I just use, when is it just a normal model problem? And basically it comes down to, if we're just talking about individuals or the population, it's going to be a normal model problem. And if we're talking about the mean of a group mean or mean of a sample, we're applying the central limit theorem. And when we apply the central limit theorem, we're saying that the sample mean itself follows a normal distribution. And kind of the key takeaway there is that if the sample mean follows a normal distribution, then most of the time the sample mean is going to be close to the population mean. And then so the confidence interval takes that, flips it around and says, if most of the time the sample mean is close to the population mean, then when I observe the sample mean at a certain location, I can be confident that the population mean is nearby. Okay, and that's pretty much the central idea of the confidence interval. If I see the sample mean here, I can be confident that the population mean is nearby, right? If we see the dog located here on the football field, we can be confident that the invisible man, invisible owner, is nearby. But that requires the central limit theorem. And so it comes down to kind of these two key ideas. One, it has to be reasonable to think that our sample that we've observed is a random sample from a large population. Now, again, getting a truly random sample from a population is almost impossible to pull off in real life. And so you have to kind of look at the study and you say, well, is it reasonable to think that my sample could be like a random sample from a population, right? So it's not really a random sample from the population, but is it reasonable to treat it like one? And if it is, then we're okay. But you might say, well, you know what, this study only looked at, people from a certain demographic, right? A certain age group or a certain socioeconomic status or something like that. And you might say, well, yeah, this is not going to work, right? You only looked at rich people or something, that could be a problem, okay? And then the other part is the sample size must be large enough, okay? And the rule of thumb is, well, first, if the population is normal, any sample is going to be large enough, right? So if you have a population that's really normal, normally distributed, approximately normal, sample sizes of 4 or 5, that's going to be fine, okay? But if the population is not normal, you need a bigger sample, and the rule of thumb is 25 or more should be good enough for most cases. In some cases, even a sample size of 25, not going to be big enough, but that's like if you have really skewed data. All right, so what we're going to do is we're going to take the concept of a confidence interval and we're going to kind of expand on it to compare two populations. All right, so rather than looking at one sample, its mean, and talking about the corresponding population mean, we're going to take a look at two samples. And based on what we see in these two samples, we want to make a conclusion about the respective populations. And in particular, what we're not doing is we're taking one sample and making a confidence interval over here and one sample over here and making another confidence interval. What we're doing is we're looking at the two samples kind of like in contrast to each other. We're saying, like, what's the difference between these two samples? And what does that say about the differences between the populations? What does it say about the difference we have between the mean of this population and the mean of this population? So here's this little diagram here. And the idea is, this is supposed to be a big entity, right? The population is this big entity that we can't observe directly. It's got population 1 has some mean mu1. Population 2 has some mean mu2. And from population 1, we draw sample 1. And from population 2, we draw sample 2. And all we get to really see, okay, we don't get to see population 1 directly or population 2 directly. We only get to see what's in sample 1 and sample 2. And so specifically, we get to see the mean of sample 1, that's x bar 1 or y bar 1, the standard deviation of sample 1, S1, and the size of sample 1, which will be N1. And then we have sample 2, and we get to see the same 3 summary statistics there. The sample mean, x bar 2, the standard deviation, S2, the sample size of sample 2, which is N2, okay? And that's what these little subscripts are, right? So to distinguish between the mean of sample 1 and the mean of sample 2, we have x bar 1 and x bar 2. And so based on what we see there, x bar 1 and x bar 2 are, I guess I'm just switching letters here, y bar 1 and y bar 2. Based on what we see in these sample means, what can we say about the population mean mu1 and mu2? Specifically, what can we say about the difference, this quantity, which is the difference between mu1 and mu2? How different are these two values? Okay, so let me give you your first view quiz answer for today. Today's first view quiz answer is the letter D. The letter D as in dog. D as in dog. D as in dog, first view quiz answer. Okay, so jot that down. All right, so this is kind of the question that we're trying to answer when we make a confidence interval about mu1 and mu2, okay? And so this quantity, mu1 minus mu2, represents the difference between the population means, okay? And specifically, what we want to know is, could that difference be equal to 0? Could the difference between mu1 and mu2, could it equal 0? And if the answer is yeah, it could equal 0, then what does that mean? Then that means the two populations could effectively have the same mean, okay? That there's not really a difference between population 1 and population 2 when we're talking about the average, right? Okay, on the other hand, we might, at the end of our study, when we do our conclusion, we might find evidence, right? So this is another possibility. We find evidence that mu1 and mu2 is different from 0. We have evidence that mu1 minus mu2 is not 0, right? So if we have evidence that mu1 and mu2 isn't 0, then that means we have evidence that the two populations have different means, okay? It doesn't mean that there's no overlap between population 1 and population 2. So for example, we could say population 1 is adult men in the United States, and population 2 is adult women in the United States. And we could be talking about like the average heights, the mean height of adult men and the mean height of adult women and things like that. We could ask, is there evidence that there's a difference between the mean heights here of adult men and adult women? Of course, when we look at individuals, you could have some women who are taller than men in the United States, adult women who are taller than adult men, and that's not an unusual thing. But we're not talking about individuals. We're talking about the mean, the average, the mean of the population. Okay, so it's a little bit strange, but this quantity itself is the parameter value that we're trying to estimate. Okay, we're not going to be able to get an exact value for this quantity because we don't have exact direct access to the populations. But what we're going to do is we're going to make an interval. We're going to make a confidence interval, and we're going to say, I believe, or I'm confident that the difference, mu1 minus mu2, that the difference between the means is somewhere between here and here, or between here and here. All right. So yeah, if we were to make a confidence interval for the heights of adult men and heights of adult women, the confidence interval for the difference could say, just for an example, could go anywhere from 4 inches to 8 inches, right? I'm just kind of making up these numbers, or 10 centimeters to 20 centimeters. And basically what we're saying is that I'm 95% confident that the average height of adult men is somewhere between 4 and 8 inches taller than the average height of adult women. Okay, so again, if we just take the population of kind of men, self-identifying men in the United States, and we just somehow measured all of these people's heights, and we got a mean, okay, it would be some number. I don't know exactly what, right? 5'9", 5'10", something around there. Okay, we do the same thing for women. We get some number, maybe around 5'4", 5'5", who knows, right? And we just say, well, what's the difference between these two numbers, right? What I'm saying is that whatever that difference is, I'm 95% confident that that difference is going to be somewhere between 4 inches and 8 inches, okay? That the average, another way to think of this is that if there's quote unquote such a thing as an average man, or an quote an average woman, what would the height difference be between these two people, these two fictional imaginary average people? And we're saying, I'm 95% confident that the height difference is somewhere between 4 and 8 inches, where the average man is somewhere between 4 and 8 inches taller than the average height of the height of the average woman there, or whatever. So it's important to make a distinction here, and we're not making a confidence interval about the average height of men alone, which is probably something around 5'10", 70 inches, or the average height of women alone, which is probably something around 64 inches, 5'4", it's a statement about the difference, okay? And so if we look at this interval and we say, you know, my interval is anywhere from 4 to 8 inches, okay? We're going to say 0 is not between the ends of my interval. And so because 0 is not between the ends of the interval, we would say we have evidence that the difference between population means is not 0. Right? Or in other words, we would say we have evidence that there is a difference between population means. All right, I just want to make sure that we're okay with all of the sentences that I've put, at least, you know, the logic and the ideas behind a confidence interval for a difference. It's not confidence interval for one mean, it's a confidence interval for a difference between means. Does this feel okay? All right, okay. 2 thumbs up, great. Okay, 3 thumbs up, okay, even better. So this is just a formula, okay? And so right here, we're going to put in the difference between our 2 samples means, mean of sample 1 minus mean of sample 2. That goes pretty much right in the middle of our interval, or it is in the middle of the interval, okay? The critical value is T star, and we're going to multiply it by this quantity, which is our standard error, okay? And the standard error is just this formula, this slightly ugly formula that we can't really do much about, but that's what it is, okay? It's, you can think of, the textbook draws this Pythagorean theorem illustration, you know, kind of S1 squared over S1 over a squared of n squared, which is S1 squared over N1 plus S2 squared over N2 and things like that. But pretty much it's just this is just the formula, okay? Your quizzes and your exams are going to be open notes, so here it is. Just mark this page so you can find it. All right, and so this is our estimated standard error. Margin of error is T star times this. So the whole plus or minus part, that's the margin of error, okay? Now, looking up the T star, the critical value T star in the T table, this is, the truth is that the degrees of freedom between 2 independent samples is kind of complicated, all right? As far as this class goes, we're just going to approximate the degrees of freedom using N1 plus N2 minus 2, you know, unless the textbook problem says use this number of degrees of freedom or something like that, just approximate it using N1 plus N2 minus 2. This is what we call a generous approximation, because if you find the actual degrees of freedom, there's the formula for it is on one of these pages. Page 211, at the bottom of page 211, 6.7.1, there's a formula. It's a bit of a mess. We're not going to bother with it. So we're just going to use N1 plus N2 minus 2. This is always kind of overestimates the degrees of freedom. If you read another textbook or something, it might say use N minus 1, just using whichever value is smaller between N1 and N2. Just do N minus 1. That's going to be a little bit more cautious. You're going to always have, you know, fewer degrees of freedom and things like that. What we're going to do is we're going to just use the generous one. And if we get some degrees of freedom that's not found in the table, we'll just round down to try to kind of undo whatever we've done. Okay. All right. So I've made up this example. I don't even know if this would be legally allowed, but let's say you're going to apply for some job, right? And I don't know, you have to work on some factory line. And so they want to make sure you can do things with your hands, right? And you have and they have this manual test for dexterity, right? And the test is going to count, you know, you get these strange blocks and you got to kind of fit them through some hole or something. And you guys say, hey, you know, how many can you do in a 1 minute period? And maybe these are tough, right? Okay, and so we give the test. We give it to some young adults. We give it to some senior citizens. Okay, 20 young adults, 15 seniors. and we time them. We say, how many of these things can you solve in a minute? All right, and so when we, at the end of our experiment, the young adults, they're able to do like 28.2 of them, that's the average, okay? So some did 28, some did 29, some did less, and some did more, and things like that. The average, 28.2, we get a standard deviation of 4.3. You go ask the seniors, how many were you able to complete? Their average is 24.3, standard deviation of 5.7, right? So just based on our preliminary data, or just the data we've collected, we have a mean of 28.2 and a mean of 24.3. And the question basically is, okay, so my samples are 28.2 and 24.3. There's a difference there. And the question is that difference like meaningful? Does it actually reflect that in the population of all young adults and in the population of all senior citizens, we would observe the same kind of difference? Or could this difference just be like a random fluke, right? Like I just happen to get these high performing young adults, and I just also happen to get these low performing seniors or something like that. That's also a possibility that somebody could argue, right? And so this is what we want to know. Does the confidence interval provide evidence that there is a difference in the average number of blocks completed by young adults and seniors in the actual population, not just in our sample? In our sample, yes, our young adults outperformed the seniors. And what we want to know, is this just a random fluke of my sample? Because we could argue that my sample is just a random, or my sample is a random sample from the population. Or is this difference between 28.2 and 24.3, is that big enough to say, yeah, you know what, this is probably something that actually exists in the population? Okay, what do you guys think? Just what kind of answers can we say? So for your reactions, you can give me a green yes for a yes, I think there's an actual difference, or red X for random fluke. Okay, all right, so most of you are thinking actual difference. We got a couple people saying could be a random fluke. Well, let's find out. We're going to we'll do the math. Oh, okay, so let me go ahead and pull up this sketchbook here. Okay, that's not what I want to do. Okay. So here is, actually, all right, let's do this here. So we will do young adults. All right, and we'll say seniors here. And so we'll go through and we'll read our thing and we'll say, all right, let's gather the data we have. So we need a Y bar, we need an S, we need an N. I'm going to put a subscript of 1 to just kind of indicate this is sample 1. This is going to be sample 2. All right, so the young adults, we have 28.2, our standard deviation 4.3, and our sample size, we have 20. Okay, seniors, Y2 is 24.3. Our standard deviation is 5.7, and our sample size is 15. Okay, so I'm going to go ahead and so my confidence interval is Y bar 1 minus Y bar 2 plus or minus T star, and my standard error is S1 squared over N1 plus S2 squared over N2. Okay, so let's go ahead and do this. So Y bar 1 minus Y bar 2, 28.2 minus 24.3. This is going to go in the center of my interval. The T star says we want 95% confidence, and my degrees of freedom, we're going to do N1 plus N2 minus 2. We're going to round down if we can't find our number here. So we're going to do 20 plus 15 minus 2. This gives me 33 degrees of freedom. Let me go ahead and pull up the reference table. So we're using the reference table under week 2. We're going to go to the critical values of the T distribution. 95% confidence, we're looking for 33 degrees of freedom. 33 degrees of freedom does not exist in the table. It exists in real life, but in the table, I'm going to round down and I'm going to use 2.042. Is that okay? So I'm going to round down from 33 down to 2.042. All right, so T star, we're going to do 2.042. So I'm going to put that right here. And then I've got to plug in all of this. So S1, 4.3 squared over 20 for N1 plus S2 squared, 5.7 squared over 15. Okay, and I need my calculator. I know I can get through the notes much faster if I just use the the pre-written numbers on the slides, but past feedback told me that it was useful for me to kind of do these things by hand here on the screen, and so that's why I do it. But if you guys don't like this, I don't have to do it. Okay. So anyway, 28.2 minus 24.3, that's going to give me 3.9 here, plus or minus 2.042. Okay, and then we're going to do this whole thing. Okay, which I'm going to do the square root of 4.3 squared over 20 plus 5.7 squared over 15. Okay, so I do that and I get 1.758. Okay, I mean, that is what I figured out here. Okay, so then 2.042 times 1.758 gives me 3.589. Oh, we'll round off to 3.59. That's fine. Okay, so I have 3.3 plus or minus, I'm sorry, this, I made a mistake here. This is 3.9. Oh dear, where's my eraser? Oh, too big. All right, 3.9 plus or minus, okay, so I have 3.9, this is a 9, plus or minus 3.59. Okay, and so this gives me 3.9 minus, what's wrong with me? Okay, 3.9 minus 3.59 gives me 0.31, 2, and then 3.9 plus 3.59, 7.49. Okay. All right, and so this is the result of the calculation. Okay. So there's the result of the calculation. I think that lines up exactly with what I have in the slide from kind of previous, from when I pre-solved it. Okay, so I get 0.31 to 7.49. Okay, so these are the so we have the numbers from the table, and then we go through and we get these values. Okay, so people in the chat are saying I should keep doing this handwritten stuff. All right, and so so that means when we make our confidence interval, we write a statement like this: we are 95% confident that on average, young adults can complete between 0.31 and 7.49 more blocks than seniors on average. Because remember, we're making a statement about y bar 1, I'm sorry, not y bar 1, mu 1, which is the average numbers completed by young adults, and minus mu 2, which is the average number completed by seniors. And so our confidence interval goes from 0.31 to 7.49. It's not dramatically over, the entire thing is not dramatically over 0, but it is over 0. So 0 is not within the bounds of the interval, okay? And so we would say we do have evidence that there is a difference between the average number of blocks completed by the two groups. All right. I hope that feels okay. Okay, so let's take a look at this next slide. So the next slide says, what if, so when I did this, I said young adults are going to be group 1 and seniors are going to be group 2, right? What if we called this young adults were group 2 and seniors were group 1? Okay. So, we got a couple questions in the chat. Okay, so one would say, okay, what would you say if 0 was in the interval? Okay, so let's say, all right, do I have a slide that covers this? Okay, maybe not. Okay, I should have done that. Sorry. Okay, so let me finish this slide and then I'll address all of your questions. Okay, so we're here. We would say if we swapped the two group labels, okay, then everything would be the same except this first part where we did 28.2 minus 24.3. That would switch around to basically 24.3 minus 28.2, and the this t star, the critical values remains the same. The standard error, we're just kind of adding these values together. That value ends up being the same. So we will end up being negative 3.9 plus or minus 3.59. And our confidence interval just becomes basically the negative version of this. We get, instead of going from 0.31 to 7.49, we get negative 7.49 to negative 0.31. And so the interpretation there would be very similar. And it would just say, we are 95% confident that on average, seniors can complete between 0.31 and 7.49 fewer blocks than average. Okay, same meaning, but it's the reference point has just changed, right? Over here, we said young adults can complete between 0.31 and 7.49 blocks more than seniors on average. And here we're saying seniors are completing fewer than the young adults on average. Okay, same thing. We're just saying young adults can do more than seniors, or seniors can do fewer than the young adults. And then, and again, because 0 is not within the bounds of the interval, we would say we have evidence that there is a difference between the average number of blocks completed by the two groups. Okay, I don't think I put this in the slides, and but let's just say, let me carve this out here. So this is my confidence interval. This is my 95% confidence interval. Now, the 95% confidence interval went from 0.31 to 7.49. Okay, what if I did a 99% confidence interval instead? Okay, so here I would have basically the same thing, 28.2 minus 24.3 plus or minus, and instead of 2.042, I would use the column from 95. Instead of 95, I would use the column for 99. So instead of 2.042, I would use 2.750. 2.750. Maybe I might do a version 2.0 of my notes for today. Okay, so for 99%, I would go from 2.042 to 2.750 based on the table here. Okay, for 99% confidence. Okay, and let me just kind of, 1.758, that number is going to remain the same, right? Times 1.758. All right, so let's go ahead and let's just take a look at what we get here. This, we're going to get 3.9 plus or minus 2.750 times 1.758. That gives me 4.83. I'll just round off to 4.83. So 3.9 minus 4.83 gives me negative 0.93. 2, and then let's change that to a plus 8.73. Okay, and then so now my statement would be something like this. I am 99% confident that the number of blocks completed by young adults on average and then this phrasing gets weird because we rarely make statements like this, but that the number of blocks completed by young adults on average is between 0.93 fewer and 8.73 more than the average number of blocks completed by seniors. Okay. And we would say, because 0 is in our interval, we do not have evidence that there is a difference between population means. Okay, and again, here we, so let me just add a note to myself, desktop, and I'll do edit notes. Okay, so I'll update today's lecture notes, just look for a version 2.0 on CCLE later, okay, with a slide incorporating this. And so again, we kind of see that, if you're willing to be only 95% confident, you can jump to the conclusion and say, oh yeah, young adults are outperforming the seniors, right? We're ready to kind of make these conclusions and say, you know what, as far as hiring practices, let's only hire the young adults. Now, you'd probably get some class action lawsuit of ageism and things like that, but just kind of pretending that, if we're just looking for kind of performance differences and things like that, if we're willing to just be 95% confident, we've got the data to be 95% confident and say young adults are can do more blocks than the seniors on average because our interval does not contain 0. On the other hand, if we want to be 99% confident in our conclusions, we got to be a little bit more cautious, right? We have to have overwhelming amounts of data before we come to the conclusion, that there's a difference between the two groups. So if we want to be 99% confident, then my interval ends up being wider and I'm not ready to make this conclusion. You say, well, I want you to be 99% confident in your conclusion. You say, if I have to be 99% confident in this conclusion, I'm not ready to just reject the seniors and say that they're performing at a different level than the young adults. Is that okay? The kind of the difference in the types of conclusions that we're making and the the resulting confidence interval that we get, how we're looking for 0 inside our interval. Is that okay? All right, I hope so. You know what? I had an example here for you guys to work through, but I think in the interest of time, I'm going to just keep going here. Okay, so you can solve this on your own as you're going through your notes. Okay. So we make an interval. Okay, and there's another important thing is that when you create your interval, and if your interval does not contain 0, we can make this conclusion. We can say we have evidence that mu1 is different from mu2, right? And kind of going along with that, there's this phrase that you might hear is we can say that the means that we observed in our sample mean y bar 1 and sample mean y bar 2, that those means are the difference between them is statistically significant, okay? That the difference, right, when we observed, okay, at 95% confidence, this difference, 28.2 and 24.3, that's a difference of 3.9. That difference of 3.9 is statistically significant, okay? If we go to the 99% confidence level, it is not statistically significant at the 99% level, or 1% significance level, but at 95% confidence, it is statistically significant. We're getting a this difference 3.9. The resulting interval does not contain 0, and therefore we're going to say the difference between our sample means y bar 1 and y bar 2 is statistically significant, or that y bar 1 is statistically different from y bar 2. But just because something is statistically significant, and this is what kind of throws people off, is that statistically significant does not actually mean it's actually important, okay? A result is statistically significant if it means that the outcome that we've observed is unlikely to be a result of just kind of random chance alone. But whether that difference is actually important or not requires, knowledge of the subject, right? So here's just this example that I'm taking from the textbook, and it's we can say, you're some kind of farmer, right? And maybe some company is advertising their fertilizer, right? They say, switch over to organic fertilizer or something, and if you do this, it's going to produce better yields in your crops. Okay, again, I don't know anything about farming, but our textbook uses a lot of farming examples. So we're going to say, all right, we're going to look for the difference between the yield with the fertilizer versus the yield without the fertilizer. Okay, but any kind of change in your system is going to be an expensive investment, right? Maybe you have to buy all new machines, and you have to train all of your employees and new methods and things like that, and it's going to be kind of an expensive thing, right? So you say, well, you know what, in order for to convince me of this investment, I need to see at least this much of a gain, okay? Otherwise, it's not going to be worth it, right? If it's less than that, it's going to take me like 50 years to break even, and I hope not to be working in 50 years or something like that, right? So you say, for it to be worth it, I need to see a gain of at least this much, of at least 1.0 in the yield, okay? And so this number, this is an arbitrary number that we've come up with, but it's a number that requires an expert opinion, okay? This is not a number that we arrived at using statistics or some mathematical thing. This is some expert who's knowledgeable in the field, who did other kinds of calculations based on their experience, and they know the market prices, or they know, things about return on investment and things like that. They came up with this number, okay? And so this is going to be some arbitrary goalpost that we're aiming for, and we want to see if we're going to get something that's that's actually important versus statistically significant. So the methods in our class can tell us whether the difference is statistically significant. Our class cannot tell you if something is important. Okay, is something actually important? That requires someone knowledgeable in the field. Okay, and so this is one thing that always kind of makes me cringe a tiny bit. Is I see all sorts of job postings asking for data scientists, and I see a lot of people kind of advertise themselves as, that they can do, they can analyze your data, and they're a data scientist and data expert. And I don't doubt these people's credentials in being able to analyze data, okay? But I do doubt that these people are going to be experts on every single field out there, right? I am not knowledgeable in, I feel very confident in my data analysis ability, but I would not consider myself an expert in hardly any field. And so if you gave me a brand new data set in a field that I'm not familiar with, I would not feel comfortable advertising myself as some kind of expert in here, being able to do your analysis. And it requires working closely with somebody who is knowledgeable and expert in the field in order to draw some kind of meaningful conclusions. All right, so here's a bunch of fictional confidence intervals and what kind of conclusions we can make from them, right? So again, for something to be worth it, we need to see a gain of at least 1.0, okay? But then for something to be statistically significant, we want to see if 0 is inside or not inside the interval. So if we create a confidence interval and it goes from 0.2 to 0.3, this is statistically significant. 0 is not inside the interval, so it is statistically significant. But does this mean that the gain is important or worth it? And our answer is going to be no, right? So you could be statistically significant, but not actually important, because for it to be important, we need to have gains over 1.0, and this is not going to be the case. Even in the best case, our gains are not going to be over 1.0. So this is not going to be important or worth it. On the other hand, if we get an interval like 1.2 to 1.3, this is statistically significant. 0 is not in the interval, so we know that this is not a result of just random chance. Is this also worth it or important? And the answer is yes, okay? Our gains are certainly going to be over 1.0, okay? Even in the worst case, we're thinking something around 1.2. So even in the worst case, it's going to be over 1.0. This is going to be this is going to be important or worth it for us to invest in. Okay. You might get an interval that looks like this, 0.8 to 1.3. Is this statistically significant? The answer is yes. 0 is not in the interval, so therefore we have evidence that it's not, that there is a difference, that it's not a result of just random chance. Is it worth it? Is it important? And the answer is we're not sure. Maybe. Okay. The true value could be anything between 0.8 and 1.3. We're 95% confident that it's anywhere between 0.8 and 1.3. We don't know if it's going to be above 1.0. We don't know if it's going to be below 1.0. We're not sure. So is it going to be worth it? We don't know. Could be yes, could be no. Okay. You might get an interval that goes like this, from negative 0.2 to 0.3. Okay. This is not statistically significant, right? This says, the difference we observed, in the population, you could actually get a difference of 0. So 0 is in the interval. It's plausible for it being the difference. And so it might not actually be statistically significant. Is it going to be important or worth it? And the answer is going to be certainly not, because even in the best case, it's going to be at best 0.3, which is less than 1.0. And depending on your data, you could even get something with a really high amount of variability, and you can end up getting a confidence interval that looks like this, which might be the most kind of confusing thing, where here your answer is that it is not going to be statistically significant. It could be as low as negative 0.2 or as high as 1.3. 0 is in the interval, so we don't have evidence that there's a difference, at least from a statistical standpoint. Is the investment going to be worth it, or is this difference important? Okay, and the answer is it actually could be. We're not sure, right? The number could be anywhere from negative 0.2, where we're actually seeing a decrease by investing in our kind of new fertilizer system, or it could be as high as 1.3, which would actually, pay off. Okay, so the true value could be over 1.0, it could be below 1.0, we're not sure. This would be kind of the most, troubling and confusing result, because, if you invest in it, maybe it pays off because the real result is something like 1.29, 1.3, or it could actually reduce your yield and end up being negative. And now, not only did you spend a whole bunch of money on this new system, but it's actually reducing your output and things like that. So that'd be, kind of a disaster scenario. Who knows, right? At least in these cases, we know, certainly we're not going to invest in the system. All right. How do we feel about this concept of statistically significant versus actually important? And again, the idea of importance depends on an expert. Somebody needs to be knowledgeable in the subject to tell you, This is actually important. All right, let me go ahead and give you your second view quiz answer. Second view quiz answer for the day is A as in apple, A as in apple. Okay, we're going to keep moving along in our textbook. So that wraps up chapter 6, and we're going to move into chapter 7. Chapter 7 is a very important chapter, and we're going to spend all of the rest of today on it, and then all of Thursday talking about chapter 7. And this introduces the concept of hypothesis testing, and we're going to start off with the t-test, which is a hypothesis test that's going to be closely, very, very closely related to the confidence intervals that we've done today. But once we establish this framework for hypothesis testing, we will expand on this and introduce a lot more of other hypothesis tests in the rest of the course. So again, statistical inference, and we just take a step back. Statistical inference is the idea or the process of making conclusions about the population based on a sample or samples of data. And the confidence interval that we covered today and also last week, that is one of the tools that we use for statistical inference. The hypothesis test is another tool for statistical inference. And we can think of hypothesis testing as some kind of framework that kind of provides this logical flow as far as what kind of conclusions we're going to make from the population. And so the first hypothesis test we're covering today is the t-test. I don't know if you guys have heard about the t-test, but this is directly related to the confidence interval that we talked about earlier today, which is the confidence interval for the difference between means. And so when we create a hypothesis test, any research question that we have about a population has to be stated as some kind of testable hypothesis, okay? And when we create this testable hypothesis, we call it a null hypothesis. And what we're going to do is we are going to test our hypothesis against the data we have observed. And that's why we call it hypothesis testing, because we have data and we test our hypothesis against this data. Basically, we say, could this hypothesis be true if this is the data that I'm seeing, right? And in order for us to be able to test a hypothesis, it has to be a specific thing, right? It can't just be some vague statement, right? If it's a vague statement, we can't test it, So if you were to see, some kind of fortune teller, if a fortune teller makes a vague statement, right? Like they're going to say something exciting will happen to you in the next, in the near future, that's such a vague statement that it's going to be impossible to kind of prove right or wrong, right? But on the other hand, if a fortune teller makes a very specific statement, right, that I can't remember what is it, Professor Trelawney said about Harry Potter, but right, you make some specific thing that says, on the night that this is going to happen, on this night, this particular event, this is going to happen to this particular person. That's a very specific claim, and we can test if that actually happens on that day to that person on that, on that night. But again, if you just kind of make vague statements, we can't really test them. So in order for our hypothesis to be testable, it's going to make a very specific claim about the population. And as far as the t-test goes, the null hypothesis is going to make this very specific claim that population 1's mean, mu1, is exactly equal to the mean of population 2, mu2. Okay, that's a very specific claim that we're saying that the mean of population 1 is exactly equal to the mean of population 2, right? And so symbolically, we might write something like this. H0, or the null, H null, is mu1, mean of population 1, is exactly equal to mu2. That would be a testable hypothesis. Okay. And when we do the hypothesis test, we start off with this null hypothesis, and we're going to just say, you know what, for argument's sake, let's pretend or imagine a world where this statement is true. okay, just for argument's sake, let's imagine a world where mu1 is equal to mu2, that population 1 and population 2 have means that are exactly equal. If that's the case, if population 1 and population 2 have the same mean, then what would our world look like? Okay, well, when you take a random sample from population 1, you get sample 1, and you take a random sample from population 2, you get sample 2. If you look at your two samples, you would expect sample 1 to have a mean, sample mean, that's very close to the mean of sample 2. You expect those two samples to be similar to each other in this scenario, right? So again, we're pretending we live in a world where the claim might be the null hypothesis is true. And if that were the case, we expect our random samples to have means that are similar to each other. We wouldn't actually expect the mean of sample 1 to be exactly equal to the mean of sample 2, but we expect these sample means to be close to each other, right? Whatever we mean by close to each other. And so, you know, when we look at our data, maybe sample 1 has a mean of 28.2. Sample 2 has a mean of 24.3, right? These are numbers that I used from my previous example. And so they don't have the exact same mean. They have a difference of 3.9. And so the question is that difference, 3.9, is that statistically significant or not, right? If the null hypothesis were true, I would expect my two samples to have pretty much the same mean, basically a difference of 0. And here I'm getting a difference of 3.9. And that's what we want to know. We want to know, is this difference of 3.9, could it just be a random fluke, or could it is it actually indicative that, you know, my null hypothesis is wrong, right? So we're going to say, you know, I know that the means of my samples are subject to randomness, right? If population 1 and population 2 do have the same mean, the question we're going to ask is, what's the probability that from randomness, we end up getting two samples where the difference is 3.9? Because that's what happened, right? And when I took my data, sample 1 had 28.2, sample 2 had 24.3. I had a difference of 3.9. The question is, could this happen by random chance? And if so, if it could happen by random chance, what's the probability it would happen, right? So we got to do some calculations, and that's what we'll cover here in just a moment. So the answer to this question, what is the probability that randomness alone could produce a difference of 3.9 or something more unusual if the null hypothesis is true, right? So what's the probability that randomness is going to produce the data that I have, a difference of 3.9, okay? That probability is known as a p-value, okay? It's the probability of basically getting the difference we observed in our sample. So here's the definition of the p-value. It's the probability of observing the statistic in our data or something more unusual if we assume that the null hypothesis is true. So in the context of our problem, the statistic we observed in our data is a difference of 3.9, right? 24.2 versus 24.3, that's a difference of 3.9. That's the statistic we're observing. We're observing a difference of 3.9. And the question is, how often do you get a difference of 3.9 or something more unusual if the two populations actually have the same mean? Okay, so we're going to go and we'll do the calculations here. But before we get into the calculations and figuring out the actual p-value, I want to think about what kind of answers we could get, right? So we could do our calculations. And it says, and so one possibility is we say, okay, what's the probability, right? So again, in our fictional world, we're imagining the mean of population 1 to be equal to the mean of population 2, right? So this is our fictional world that we're imagining. And we're saying, if in this world, most of the time, when I take two random samples, these two random samples should have the same mean, okay? and I happen to get a mean of a difference of 3.9. And the question is, how often does this happen? What's the probability I get a difference of 3.9? So we're going to do some calculations. Now, before we actually do those calculations, let's just think about what our answers could mean, right? Let's say we do our probability calculations and it says, you know what? You should rarely get a difference of 3.9. Getting a difference of 3.9, that's going to happen like 1% of the time. I mean, it could happen, but it's pretty rare. It's going to happen only like 1% of the time. What would that actually mean? Okay, so one outcome is that, you know, you do your calculations, the p-value ends up being small, right? So this is one possible outcome. You go through your calculations and you say, you know what, if the two means were actually equal, could you get a difference of 3.9? And the answer is, it's not impossible, but it's only going to happen like 1% of the time. Okay, so we're going to say it's unlikely. It's unlikely for us to get a difference of 3.9. Okay, so then what does that mean? That's what I got. I got a difference of 3.9, right? According to my calculations, this should happen. This is an unlikely thing to happen, right? And the fact that it did happen then gives me evidence that the claim made by the null hypothesis is wrong, right? And therefore, we're going to come to the conclusion that the reason why we saw a difference of 3.9 isn't that we got this lucky 1% scenario, but just that this hypothesis that I started off with, this presumption about the world, that was actually wrong. That population 1 and population 2 aren't actually equal to each other, and I didn't get this weird 1% outcome where I got a difference of 3.9, but rather that initial assumption was wrong, and that's why I got this difference of 3.9. Okay, and so in that case, we would reject the claim made by the null hypothesis. Right? Another way you could think of it, right, is you know, maybe there's some game of chance, okay? And if you, let's say you're playing a game of chance with a stranger, and they say, you know, I'll give you, this is a game of chance, we have a 50% chance of winning, right? You play one game with the person, the stranger wins, okay? And you go, okay, maybe I just got unlucky, right? But what if you played 100 games with this person and this person won all 100 games? Do you think this person is playing fairly? And the answer is going to be no, right? The person could argue, no. I just happen to get really lucky. I happen to get lucky and I happen to win every single game of chance 100 times in a row, right? Is that impossible? It's not impossible, right? According to randomness, it is technically possible, but that's an extremely unlikely scenario. And because it's so unlikely, because the probability is so low, you know, the rather than saying, you know what, we're going to give you the benefit of the doubt, you're playing fairly, and you just happen to get really, really lucky, and we just happen to get really, really unlucky, and that's why we won 0 and you won 100. Rather than saying that, we're going to say, you know what, I think this presumption that you are playing fairly is wrong, and that's why you're winning so many, okay? We're basically doing that. We're saying the probability of my data is low, and rather than saying we just got this really lucky or unlucky sample, is just that this initial presumption was wrong, and that's why we're seeing this data. Okay, so that's one outcome. Okay, another possible outcome is that you do your calculations and the p-value is large, right? You say, well, if the two populations have a mean of 0, or have no difference between the two means, that the difference is 0. You know, could I get a difference of 3.9? And maybe you do your calculations and it says, oh yeah, difference of 3.9, that's not that unusual. That's going to happen like 23% of the time. You go 23% of the time, that's like over 1 in 5. And so you would say, you know what, we got a difference of 3.9. You know, I would have expected a difference of 0, but maybe 3.9 is not all that unusual. Okay, maybe it's not all that unusual. And so we're going to come to the conclusion that we don't have any reason to believe that mu1 is different from mu2. Okay, this doesn't actually mean that the two populations, mu1 and mu2, are equal, that the two populations have the same mean. It's just at this point in time, we don't have enough evidence to say anything against that claim. Okay, so we're not going, in this case, we are not going to reject the claim made by the hypothesis, right? This would be, you know, again, you can imagine playing the game against the stranger, and maybe you play 2 games against the stranger. He says it's a even, you have an equal chance of winning and losing, and after 2 games, you know, the stranger has won 2 games and you lost 2 of them. Does that mean that the stranger has cheated? After 2 games, it's inconclusive, right? The stranger could have just gotten lucky, right? There's about a 25% chance that something like that could happen, right? And then you just say, okay, well, 2 games, that's enough. Does that, you know, it doesn't absolve the stranger. It doesn't mean the stranger's been playing fairly. Stranger could have been cheating, but 2 games is also not enough to kind of prove that the stranger is cheating. So, all right, and so, you know, the decision of whether or not we're going to reject the null hypothesis, okay? Whether or not the p-value is large, considered large or not, is determined by this arbitrary value that we call our significance level, alpha. Okay? And basically the rule is, if your p-value is less than your significance level, the significance level that you've chosen, the p-value is going to be considered small. And that means our data is unlikely to be observed if the null hypothesis were true. And therefore, the fact that we actually did observe this data is going to lead us to reject the null hypothesis. And on the other hand, if your p-value ends up larger than your significance level alpha, then we would say the p-value is considered to be large. So even if the null hypothesis were true, our data is not considered to be an unusual result, and we do not have reason to believe that the null hypothesis is wrong, and we would not reject the null hypothesis, okay? The choice of the significance level alpha is often arbitrary. A common choice we use is alpha is 5%. This has somehow become the standard choice that we use. We often see alpha 1%. That's also a common choice. Not as common, but sometimes does happen, is using alpha equal to 10%, but I would say this is not frequently seen. But again, your choice of significance level is a bit arbitrary, and people could say, I want to use a 7% or a 4% or, you know, 0.5%. So whatever number you choose is really up to you. And we probably just have a bias towards 5% because, I don't know, we got 5 fingers on our hand or something. So it's a little bit arbitrary numbers. We just go off of arbitrary numbers all the time. When we think about hypotheses, it's important to remember that hypotheses are always going to be statements about the population, okay? We're never making statements about samples. So you never want to say a statement, you know, the sample mean is this or something like that, okay? The null hypothesis is always going to be the hypothesis that we're testing, and the null hypothesis is always going to have an equal sign. It's always going to have an equal sign. The alternative hypothesis, so hypotheses often will generally come in pairs. And so you have your null hypothesis, which will have an equal sign. And then the alternative hypothesis is kind of what must be true if the null hypothesis is wrong. And you have a selection there. You could have a non-directional hypothesis, basically what we call a 2-sided test, that will have a not equal sign. Or you could have a directional hypothesis or a 1-sided test, okay? And whether you use a 1-sided or 2-sided directional or non-directional test is going to depend on how the question is written. So if you have, your null hypothesis always has an equal sign. We're going to make the claim that population 1 and population 2 have the same mean, okay? And depending on how the question is written, if we're just interested in just the general possibility that the means are different, okay, we would use a non-directional alternative. Our alternative would look like this. HA is that mu1 is not equal to mu2. It would be interesting to us if we find out that mu1 is larger than mu2. It would also be interesting to us if we find out that mu1 is less than mu2, okay? But in some other situations, you're only interested in kind of one side or one outcome, right? And in these cases, you would use a directional alternative. So you might have an alternative where the null hypothesis is always going to be this, but your alternative could be mu1 is greater than mu2. And that would be the case if you're only interested in population 1 having a greater mean than population 2. Or your alternative could be mu1 is less than mu2, right? So here's an example, right? Let's say you work for some pharmaceutical company and you're part of a team that's trying to develop some product to lower blood pressure, right? You say, you know what, we need a better drug on the market that's going to lower blood pressure. Okay, so population 1 will be people who receive the treatment, who receive this experimental medication. Population 2 is going to be people who receive placebo. And what we want to see is if the product helps reduce blood pressure, right? So the null hypothesis, we're going to start off, the null hypothesis is basically that your drug doesn't work, that the drug is no different from placebo, that the effect of the drug, mu1, is the same as the effect of the placebo, mu2, okay? And then your alternative is that people who use the drug are going to have lower blood pressures than those who take placebo. That's kind of the whole point of the drug, right? The whole point of the drug is to lower blood pressures. So you want to see that the mean of people who take the medication is going to be lower than the mean blood pressure of those who use placebo, okay? Let's say you go through some experimental study, right? You get some volunteers, you know, they participate, they sign waiver forms, and they do all of this, you spend some money. And in your preliminary study or in your study, you find out that the mean blood pressure of the people who took the drug actually ends up higher than the mean blood pressure of people who use the placebo, right? This is like your nightmare scenario. You said, oh, I want to create a drug that's going to lower blood pressure. But then when you gave the medication, the people end up actually getting higher blood pressure than those who take the placebo, okay? At this point, you're just going to stop the study. You're not going to say, well, we need to collect more data or something, right? You're just going to say, uh-oh, this is not working. There's no point in continuing the analysis, okay? You're just going to come to say, you know what? We don't have, based on our initial data, we don't have any evidence supporting the idea that the drug is effective at lowering blood pressure, okay? So you want to see, that you're testing this hypothesis that that mu1 is less than mu2, and you know, when you collect data, y bar 1 ends up being greater than y bar 2. Your data does not line up with the directionality of your alternative, right? And so you're going to say you have no evidence to support the alternative. Does that kind of make sense? What's happening here? So in some scenarios, depending on what you're looking for, you're only interested in kind of one outcome, right? In this case, when you're trying to develop a medication to lower blood pressure, you're not interested. Okay, you don't want to see the medication increasing blood pressure. Okay, so let's revisit this exact data and scenario, right? So we're going back to the company that's doing, you know, possibly some kind of illegal job application. I don't know what I don't know. Maybe it's fine. Okay, maybe manual test for dexterity for job application, that's probably allowed. But then to do, you know, to specifically say, well, you're in the young adult group and you're in the senior group, that's probably something, a lawsuit waiting to happen. Okay, so here's the data we've collected, and I've summarized it in this table. And so what we want to do is, rather than creating a confidence interval, is we're going to perform the t-test. We're going to perform the t-test to see if we have evidence that there's a difference between the number of blocks completed by the young adults and the seniors, right? So we get a difference of 3.9, and we want to know, is that difference, is that statistically significant? Does that provide evidence against the null hypothesis? Okay, so when we write our hypotheses, okay, so remember, when you do this, in all scenarios, okay, when you do a t-test, your null hypothesis is going to be mu1 is equal to mu2, right? So we can say mu1 is going to be the mean of young adults. All right, so you should always kind of label what your group values are. Mu2 will be the mean of seniors. Okay, and so our null hypothesis is always going to be this. This part is always easy. The alternative, now we have a choice. Should I use a greater than sign, less than sign, or not equal sign? And in this case, we are not we're not going to start off with some kind of hypothesis that one group is going to be better performing than the other group. It would be interesting to us if the young adults did more than the seniors. Excuse me. It would also be interesting to us if the young adults completed fewer than the seniors. Okay, so either outcome would be interesting to us. So in that case, because we're interested in either possibility that one is greater than the other, or is one is less than the other, we're going to do mu1 is not equal to mu2. This would be using the not equal sign means we have a non-directional or two-sided test. All right, and so the next part is calculating the p-value. Okay, the p-value again is the probability that we would observe a sample with a difference like that of our data, a difference of 3.9, or something more unusual if the null hypothesis were true, right? So if the null hypothesis were true, we would expect y bar 1 and y bar 2 to be equal to each other, but we got y bar 1 is 28.2 and y bar 2 is 24.3. We get a difference of 3.9, right? And so the question is, what's the probability of getting a difference of 3.9 from just kind of random chance? How often does something like that happen? Okay, so in this case, we're going to calculate a test statistic. Okay, so the test statistic is, it's a t-test, so we have a t-statistic. And this is a lot like kind of a z-score, except it's going to be the difference between our sample means, y bar 1 minus y bar 2, and we're going to divide by our standard error. Okay, so our standard error, this is the same formula for our confidence interval, S1 squared over N1 plus S2 squared over N2. So the square root, to go back a couple slides here for the values. Okay, so we've got 4.3 squared over 20 plus 5.7 squared over 15. And I know I've done this calculation before, but we'll just go ahead and do this. All right, so we got 4.3 squared over 20 plus 5.7 squared over 15. Okay, so this gives me 1.758. This is my standard error. 1.758. Okay, so my test statistic T, I've got 28.2 minus 24.3 divided by my standard error, 1.758. So this becomes 3.9, a difference of 3.9 divided by 1.758. My test statistic, 3.9 divided by 1.758, 2.218. Okay, this is my test statistic T. I think that's what I've got in this slide here. Yep, 2.218. All right, and so we are going to look this value up. 2.218, we're going to go to our T table. We're going to look up our degrees of freedom is N1 plus N2 minus 2. So we've got N1 plus N2 minus 2. I've got 20 plus 15 minus 2. I have 33 degrees of freedom. When we go to our table, we're not going to find 33 degrees of freedom. So, you know, we end up rounding down to 30. Okay, so we go to our table. We're going to look at 30 degrees of freedom. We're going to look up this value, 2.218. Now, how we use the T table is quite different from how we use the Z table. Okay, so the normal T distribution looks a lot like the normal distribution, and what I'm going to do is we are going to zoom in on this part of the T distribution. Okay, so we're going to look at this kind of tail here, and this, I think this is the picture that kind of shows up in at the top of the table, right? It just says what's this upper tail probability and all of this business here. Okay, so what we're looking for, our test statistic is 2.218. Okay, that's our test statistic, 2.218. And what we're looking for is, you know, we're looking for the area beyond 2.218. And because we have a two-sided test, we want to look at the area beyond positive 2.218. And we also want to look at the area beyond negative 2.218. Okay, we want to look at the area beyond positive 2.218 and the area beyond negative 2.218. Okay, so this is my test statistic T. T is 2.218. And the idea here is I've got this normal, or not normal, T 2.218, and I'm going to go negative 2.218. And I want to know how much is beyond that way, how much is beyond this way, okay? We're looking at both tails because the alternative has a not equal sign. Okay, not equal sign means two sides, 28. Okay, we have a question about the degrees of freedom. What if we get 38 degrees of freedom, right? Let's say you have n equals 20, n1 is 20 and n2 is 20, you get 20 plus 20 minus 2, you get 38 degrees of freedom. So remember I said the n1 plus n2 minus 2 is a generous value, okay? And because it's kind of generous, 38 degrees of freedom, just to be safe, we always recommend you round down. Now, the truth is the actual degrees of freedom is probably some other number, maybe 35 or 34 or something like that. But we're gonna, you know, do 30. So if you get 38 degrees of freedom, just to be safe, I would still recommend rounding down to 30 degrees of freedom. Okay, you go, you know, 40 degrees of freedom, that's closer, but just to be safe, because we're being generous with that number, just round down anyway. Okay. All right, so I'm going to zoom in. What does a degree of freedom generally represent? Oh, this is a tough question. Let's see. What I'll give you like the explain like I'm 5 answer. Okay. Every time you have to estimate a value from a sample, we use up what's called a degree of freedom. And so we could this is a tangent here, but it's worth going into. So, you know, we could pretend we're going to play some kind of game. Hang on, what's going on? Okay, yeah, just wait until I'm done with this. Okay. All right, so we can imagine we're playing some kind of game where I say, you know what? Let's pick 10 numbers as a class, and I will guarantee that the mean of those 10 numbers will be 100. Okay, that we're going to pick 10 numbers as a class, and I can guarantee that the mean of those numbers will be 100. And you go, really? And I go, there's a catch. You guys get to pick the first 9 and I get to pick the last one, okay? And if we say that, then I think we can see how this is possible, right? So, we can go through the class, you say, at the first, I want my first number to be, 72, and I want my another number to be, 280, and another number to be -5 million, and another number to be, 374,000 or something. And you guys can pick 9 numbers to be whatever they want. And as long as I get to pick the very last number, the 10th number, I can guarantee that the mean, the average of all 10 numbers, is going to be 100. Okay. And so that kind of gets the idea that when you have 10 data points, you have n-1 or 9 degrees of freedom for this scenario. Okay. And it's a little bit of again, that's your explain like I'm 5, but it's the idea that if you have a statistic that you need to get, like the mean, and you know that the mean is going to be something, you have n-1 degrees of freedom. Now, it gets more complicated. And if you have to get the mean and the standard deviation, then it's kind of the idea. You can play a similar game where, as long as somebody gets to pick the last 2 numbers, you can kind of guarantee certain properties and stuff like that. And it kind of works out conceptually a little bit more complicated, but that's a good enough answer for now. Okay. All right. So back to this thing, right? We're looking at our chart now, and we want to figure out, okay, here we've got this number 2.218, and we're going to go to the table. We want to go to the table and we go, what is this area, right? We want to go, what is this area? And whatever area this is also going to be the same area. Okay. And so when you go to the table, we're going to kind of zoom in on this zone. Okay, that's what we're going to do. We're going to zoom in on this zone. And this is like really hard to see. Okay, but here, this is, I've just cut out from the table. I cut and pasted this line for 30 degrees of freedom, right? It starts off at 0.854, 1.31, ending at 3.646. Okay. And the idea here is if you zoom in on this lower tail here, okay, for 30 degrees of freedom, if I go to, if you look at the headings of the table, if you go to the headings of the table, they have this, the column headings say upper tail probability, okay? And the idea is if you were to draw a line at this number 1.955, and you shade everything to the right of 1.955, the amount you would shade in the upper tail, that area would be 3%. I hope you guys can see this. And then if you go farther away from 0, so instead of 1.955, you go farther away to 2.147. Sorry, I skipped a number here. But if you go to 2.147, then the amount in this upper tail is 2%. Okay, everything to the right. And if you go even farther away from 0 to 2.457, the amount in the tail, so it technically goes off to infinity, is 1%. Okay, so you have 1% to the right of 2.457. If you go to the right of 2.147, you have 2%. And if you go to the right of 1.955, you have 3%. Okay, so technically, this area here is like 1%. This area here is 1%. This area, if it goes on forever, is also around 1%. This chunk, and this chunk are equal sized here. Okay. All right, is that okay? Just the translation of how this table is working. So this upper tail probability, wherever this number is, if you draw a line and you shade everything to the right, it corresponds to the upper tail area, right? So the area to the right of 1.955 is 3%. Area to the right of 2.147 is 2%. Area to the right of 2.457 is 1%. Okay, and there's other things. If you go even farther away to 2.75, you get 0.5%. If you go to 3.646, you get, I don't know what that is, 1/2 of 1,000, okay? 5 10,000ths. And so our number is 2.218. So I'm zooming in. 2.218 is between 2.147 and 2.457. Okay, so area to the right of 2.457 is 1%. Area to the right of 2.147 is 2%. And our number is 2.218. So the question is how much is to the right of our number of 2.218? And the answer is, well, I don't know. I don't know the exact value, okay? But we can do what we call bracket it, okay? And we can say the area, whatever it is, has to be between 1% and 2%, okay? Because I'm closer to 0 than 2.457, so I know I have more than 1%, but I'm farther away from 0 than 2.147, so I have less than 2%. So whatever it is, it's got to be some number between 1 and 2%. Okay, looking at this picture, I'd probably guess like 1.8%, but you know, it doesn't matter. We're just going to say it's something between 1 and 2%. Okay. Do we feel okay about that? Bracketing our tail area. All right, and again, because we have, so this area, okay, we don't know. We're going to say it's something between 0.01 and 0.02. Okay. All right, and this thing, this is the same, all right? So the total area, which is going to be my p-value, is between 2% and 4%, right? One tail is between 1 and 2%. The total area has to be, is going to be double that. So the total area is going to be between 2% and 4%. Let me go ahead and give you your last view quiz answer. Last view quiz answer is the letter B. B as in bear. B as in bear. B as in bear is your last view quiz answer for today. All right, is that okay? This whole process of getting a p-value between 2 and 4%. What happened here on my notes? Okay, showed up down there. Okay. All right, so this is what we say, right? So if our p-value, whatever it is, something between 2 and 4%, you know, we've chosen some significance level. Let's just pretend our significance level is 5%, okay? Here, our p-value is less than our significance level, okay? Our p-value, remember the significance level is just this arbitrary number that we've selected that says, you know, if it's bigger than the significance level, it's going to be considered large, and if it's less than that, it's going to be considered small. So here we're going to say our p-value is considered to be small. And that means if the null hypothesis were true, right? The null hypothesis states that there's no difference between population means. If the null hypothesis were true, then the difference we observed, 3.9, is unlikely to happen from random chance alone, because it only happens between 2 and 4% of the time. And according to our significance level, anything happens less than 5% of the time, we're going to consider to be an unusual outcome. And so the fact that we did get this difference of 3.9, which we're going to consider unusual, tells us or suggests to us that this initial hypothesis is wrong, that the null hypothesis that the two means of the populations are equal, we're going to say that that hypothesis is wrong, and we're going to conclude that there is a difference between the two population means, that this 3.9 is not just a result of random sampling from sample 1 and random sampling from population 2, but just that actually, if you look at population 1 and population 2 itself, there actually is a difference, that difference of 3.9. Okay. And so, you know, I think at the very beginning of the class, I said, you know, who thinks this difference 3.9 is suggestive of a difference? Okay. And some people said, yes, it's suggestive of a difference. And other people said, no, it's not. And you guys both could be right, if you're just operating with different levels of significance, right? So if you're operating with a significance level of 5%, then yeah, you would say that difference 3.9 is significant. If you were operating with a 1% level of significance, then your p-value is actually greater than that. And you would say, well, I'm not ready to reject that thing. So you might be operating with a different level of significance, and you guys both could be right. Okay, but here with a 5% level of significance, we would reject the null hypothesis, and we would come to this conclusion. Our data provides evidence that in the population the mean number of blocks completed by young adults is greater than the mean number of blocks completed by seniors. Say that. Okay. Okay, so this is another example. We got 7 minutes. Okay, I think we can do it. We can do this. All right. And so I'll go ahead and I'll work through this. Okay. We'll work through this. All right. So actually, let's save some time here. I don't know if this is actually saving any time. All right. So we've got group 1. Didn't put too much effort into this because I just came up with the generic names, group 1 and group 2, with no backstory here. Okay, so number 1, we're going to write the hypotheses. The question says, is there evidence that the mean of population 1 is less than the mean of population 2? Okay, is less than the mean of population 2. All right, so here, when we write our hypotheses, the null hypothesis always, mu1 is equal to mu2. The alternative, because it says, do we have evidence that the mean of population 1 is less than the mean of population 2? We're going to do mu1 is less than mu2. Okay. All right. Here it says find the standard error. So this is just a matter of kind of plugging in values into our standard error formula, S1 squared over N1 plus S2 squared over N2. It says find the test statistic. So I'll go ahead and I'll just write all of these formulas. Test statistic is y bar 1 minus y bar 2 divided by the standard error. This is our t statistic. Find the p-value. We'll have to do that after we find the test statistic, and then we'll make our conclusion. Okay, so let's go ahead and calculate the standard error by plugging in our numbers. We got 6.5 squared over N1, 10, plus 8.4 squared over N2, which is 14. So we'll go ahead and do this. 6.5. What is going on here? 6.5 squared divided by 10 plus 8.4 squared divided by 14. Okay. 3.044. That's my standard error. 3.044. All right. And my test statistic T is going to be y bar 1, 44, minus y bar 2, 47, divided by 3.044. Okay, so in the numerator, I'm going to get negative 3 divided by 3.044. Okay, so what do I have? Negative 3 divided by, I'm just going to use the answer that was plugged in there. I'm going to get negative 0.985, negative 0.986. This is my test statistic. Okay. For degrees of freedom, I've got N1 plus N2 minus 2, 10 plus 14 minus 2, 22 degrees of freedom. And let's look up our value, negative 0.986. So we've got 22 degrees of freedom. Okay, so our table only has positive values, okay? But it's symmetric. Our table is symmetric. So even though I only have positive values and my number is negative, we can just basically what the picture looks like, right? So here I'm at negative 0.986, right? And I want to find this area over here. But the table only gives gives me the positive side. Okay, so I'm going to just look up positive 0.986, and it's going to give me this area. The table gives me this, which is equal to this area over here, right? So I'll go ahead and do that. Okay, so oh yeah, all right, what am I doing? 10, 14, 20, okay, 22 degrees of freedom. We're looking at 9.86 or 0.986. 20, sorry, I'm having so much trouble here. 22 degrees of freedom, 0.986 is between these two numbers, which means the corresponding area is between these two headings. So this is going to be between 0.10 and 0.20. Okay, 0.10 and 0.20. Okay, and because my alternative has only a less than sign, this is a one-sided test, right? The alternative has a less than sign. Okay, so this is a one-sided test. I am not going to double my area. Okay, so my p-value, whatever it is between 10% and 20%. Right? Does that make sense? Everything so far so good? The p-value I arrived at is something between 10 and 20%. Okay, I think that's what I have. Here's my hypotheses. The calculations, I think we got the same, 3.044, negative 0.986. And we look this up, and so our lower tail probability is somewhere between 10 and 20%. So my p-value, whatever it is between 10 and 20%. So far, I've done my calculations correctly. Okay, and so the last slide is going to be our conclusion. If our significance level is 5%, right, our p-value is greater than our significance level, whatever it is. It's some number between 10 and 20%. Our p-value is greater than that. So we do not reject the null hypothesis. Our p-value is greater than that. So that means we do not reject the null hypothesis. And that means we do not have evidence that the means of population 1 and population 2 are different, okay? Even though our sample means aren't exactly the same. So even though we got one sample mean was 44 and the other one was 47, because of kind of the standard deviation that we have observed here, it's not enough for us to make a conclusion that the two populations have different means. Okay, so right now we're going to say the p-value is greater than alpha. Do not reject the null. All right, and so that's it for today. All right, so this is just kind of your introduction to hypothesis tests, and so we'll end here. We got a lot more to discuss about hypothesis tests. We got a deep dive coming up on Thursday. So have a good night. We'll see you guys on Thursday, and we'll see you then. So, all right, thank you and good night.